Okay, so today we're going to talk about chapter 17.2, which is all about properties of mechanical waves. Last time we talked about the three types of mechanical waves, transverse, longitudinal, and surface, and today we're going to talk about properties that all of those different kinds of waves have. So all waves have properties that define their size, their shape, and the amount of energy they convey. These properties are based on the periodic motion of waves. That means that they repeat their motion at regular time intervals. So if we imagine that each of these lines represents 1 second, we can see that the wave comes back to the same place every second. It comes back to the 0 point every second. And every 2 seconds, it is come back to the same place and moving in the same direction. It's moving up. So you can see that this motion repeats itself every 2 seconds. This part of our wave is the same as this part, which is the same as this part, which is the same as this part. That's what periodic motion means. It undergoes the same motion over a set time interval.
And this picture is interesting because this is
now the first property that we're going to talk about is a period of a wave. But there are other properties we're going to talk about as well, which are frequency, wavelength, speed, and amplitude. And you may have heard these words used before, especially words like frequency and wavelength, but they may have been used in a different way because often in English, we use scientific words in a very unscientific way. And the scientific term of that word means a different thing, just like how the scientific physical definition of the word work means a very different thing than the English definition of work. Now, the period of a wave is the time required for one cycle. That is, a complete motion that returns to its starting point. So, if you take a look at this picture right here, this is showing us a picture of a wave. And the amount of time it would take for the wave to go from this point to this point, meaning for it to go down and up and then back to the 0 point again, that is the period. The period's the amount of time it takes to complete one there and back.
So that it was stretched out and then let go.
Now, a frequency is exactly the opposite of a period. It turns out that in order to calculate the frequency, you take the period and you do 1 divided by the period. So 1 over the period is equal to the frequency. They are literally inverses of each other. And the frequency is the number of cycles a wave completes in 1 second. So if the period is how many seconds it takes for 1 cycle, the frequency is how many cycles it is in 1 second. And you can see from our picture here that the closer together the tops of the waves are, the higher the frequency. And what that means is, in 1 second, more of these are going to pass by than in this picture. If we say 1 second is the time from here to here, you can see this only has 1 full wavelength that passes by. This has a little bit more than 1, and this has a little bit more than 2. So the more wavelengths that pass by in 1 second, the higher the frequency is going to be. What that means is, if it has a very high frequency, it has a very low period, because it doesn't take very long for 1 cycle to be completed. So that's 1 cycle in this wave. This is 1 cycle in this wave, and this is 1 cycle in this wave. It doesn't take very long for the shorter wavelengths to undergo 1 full cycle.
But some dogs can pick up P waves.
The wavelength, as I just mentioned, is the distance between a point on one wave and the same point on the next cycle of the wave. So you can see this is 1 wavelength, down and back. So it's from 1 point to the same exact point, 1 wavelength away. This is a longer wavelength because there is a farther distance between these 2 points. Now, we do not have to measure the wavelength from the tops of the waves or from the bottoms of the waves. We can measure the wavelength from wherever we'd like. We just have to make sure that if I measure it from the middle of the wave over here, I measure it from the middle of the wave over here, and it is in the same spot from where I started. I cannot start here and end here. That would not be 1 complete wavelength. It has to be in the same spot.
And so an object that is sitting in a material that has surface wave
Now,
running
wave
through it
speed
will actually move
is
in a
how fast
circle.
that wave is traveling
It will
through a
first move
medium.
to the side and then be pushed
And
up, and then
there
it will
is
be
an
pushed
equation
back
that we
in the
can
opposite
use to
direction
solve
and
how
down,
fast
and it will
a
lob
wave is
in a
moving.
circle.
And that is to take
So
the
it's kind of a
wavelength
combination
of
the
that
two other
wave
kinds
and
of,
multiply it by its frequency.
mechanical waves.
Now, the speed of a
Here are
wave
your homework
really
questions,
only
page
depends on the
5 of
medium
4,
in which it's
questions
traveling.
1, 2, 4,
The
and then
denser the
connecting
medium,
concepts.
the
Please
faster the
finish
wave
these
will
up
travel.
and,
However,
have them ready to turn in
if
tomorrow.
we assume that the speed of two waves is the same, we can say that the wavelength is inversely proportional to the frequency. What that means is, if I play a sound wave through air and it has a very, very low frequency, it's going to have a pretty high wavelength. If I play a sound through that same air traveling at the same speed that has a very high frequency, it's going to have a very low wavelength. So, for the same speed, as one of these increases, the other decreases. That's what it means to be inversely proportional. Now, let's do an example of how to use this equation. So, one end of a rope is vibrated to produce a wave with a wavelength of 0.25 meters. The frequency of the wave is 3 hertz. What is the speed of the wave? So, the equation we're going to use is the speed is equal to wavelength times frequency. We haven't gone over the abbreviations for these things yet or what their units are. We'll cover that in class with our concept and equation charts. So, if we're looking for the speed, we have to take the wavelength, which is 0.25 meters, and we multiply that by the frequency, which is 3.0 hertz, and 0.25 times 3 is 0.75. And because we were just looking for speed, the appropriate units for 0.75 are meters per second. So it's a pretty straightforward equation. You just take what you're given and plug it in where it belongs. The last property that mechanical waves have is the amplitude. And the amplitude of a wave is the maximum displacement of the wave from rest position. What that means is, from a 0 point, where if we were not applying any energy, this material would be flat, the farthest it moves from that point is its amplitude. So in this low energy wave that has a very small amplitude, that's our amplitude. This high energy wave, this is our amplitude. You can see from the 0 line up to the top or from the 0 line down to the bottom, they're the same. They,
so an example of this, whenever
we
hear the word
the
waves,
bigger the amplitude, the more energy a wave has. So if we have two waves that have the same frequency, like these two waves do, but one has a much greater amplitude, that means it has more energy. This is exactly what volume is. The higher the volume is on a sound, the larger the amplitude of those sound waves.
Transverse waves are
so just to recap, let's go ahead and label the different properties of waves in this picture. If we measure how far the wave is from one point to the same point on the next peak, this is what we call the wavelength.
And you can see that the rope
if we measure how long it takes for a wave to go out and back to the same point, the amount of time to do this is the period.
But the energy coming
if we measure how many of these waves pass by in 1 second, so we say this is 1 second, this is what we call the frequency.
A transverse wave. Some examples of transverse waves are
and if we measure how high or how low that wave goes from the 0 point, this is what we call our amplitude.
The energy moves to the side, and so that is an example.
And however fast this is moving through our medium is the speed of our wave.
This picture is interesting because this is not actually how guitar strings work.
These are your homework questions. You may need to look at your book, but most of the information should be right in this video. So please answer the questions and have them ready to turn in tomorrow.